Hello, this is sixth numerical on Euler's formula. First, see this numerical. Numerical is a T section 150 mm, 120 mm and 20 mm is used as a strut of 4 meter long with hinge at its both end. Calculate the crippling load. Crippling load, that means buckling load, and if Young's modulus for the material be 200 GPa. So our problem statement in that numerical is this buckling load, and we all know that formula of this buckling load is pi square EI upon LE square. This pi square is constant, E is Young's modulus that is given in numerical, and this LE is effective length that is depend upon end conditions, and in these numericals they are given us end condition, both ends hinged. That means effective length is equal to actual length, and actual length they are given us in numerical, actual length is 4 meters, so this effective length is 4 meter. So this is also given quantity, this is given quantity, this is constant, so only we need to find this I. And see, this is T section, and we always find this I as a x axis and y axis, and this T section is symmetrical about y axis, but this is unsymmetrical about x axis. So remember that moment of inertia is, and least moment of inertia we will consider here in this crippling load formula. So first find that moment of inertia. Finding moment of inertia is crucial point in this numerical. So for that, first we need to find centroidal axis. Centroidal axis, that means neutral axis of this T. Neutral axis. And we all know that neutral axis formula, we had seen this in our previous lectures. This neutral axis is formula is, first write position of neutral axis. So here neutral axis formula is, neutral axis denoted as y bar, and the formula is a1 y1 plus a2 y2 upon a1 plus a2. a1 y1 plus a2 y2 upon a1 plus a2. What is this 1 2? 1 2, that means this. Let us consider this as a 1 and this as a 2. So a1, that means area of this portion, this rectangle. a2, that means this above flange portion. So area of that this rectangle is this 20 and this 120. We just put in this numerical. Y bar is equal to a1 is 20 multiplied by 120, and y1 is, y1 we will measure from this point. Let us consider this as a PP, and up to here y1, that means 120 divided by 2. y1, that means like center of that rectangle, center of that one rectangle. So total height of that rectangle is 120 divided by 2, that means this is 60 mm, plus a2 is, so see, a2 is this rectangle flange portion. So area of that flange portion is, this is rectangle, that means 150 into 20. And y2, measure from that base P, measure from this region. So this y2 is total this 120, from this to this 120 plus 20 by 2. This total is 20 divided by 2, that up to here 20 by 2. This is y2. So 120 plus 20 by 2, 120 plus 20 by 2, that means 130. Again a1 plus a2 denominator. So this position of neutral axis is, calculate it with the help of calculator. 20 into 120 into 60 plus 150 into 20 into 130 divided by 20 into 120 plus 150 into 20. So it is 98.89 mm. And this is nothing but the position of neutral axis from that base. So from this base, this position of neutral axis is 98.89 mm. Now calculate moment of inertia about Ixx, and Ixx is nothing but this region. For that one portion and two portion, for one portion Ixx is like this xx. So Ixx moment of inertia, find first for that first rectangle, for that wave portion. Xx like Ixx, xx like parallel to xx, 20 as it is. So write 20 multiply by this length, height of this wave is 120, so 120 cube divided by 12, because of it is rectangle, plus why plus, because this is symmetrical about x axis. So this neutral axis is away from that original axis, wave portion axis, so that's why this plus area of that wave portion, 20 into 120. And remember this here, this is multiplication. Right, notice that addition subtraction, where we take addition, where we take subtraction, that is also important. So here it is multiplication, and this value is nothing but the square of distance between neutral axis and that original centroid axis of that only wave portion. That means this, between this total T section neutral axis and only that wave portion neutral axis, distance between that. So total T section neutral axis is 98.89 and only that wave portion neutral axis is 60 mm. So and only distance between that, so 98.89 minus 60. So this is only about that wave portion. Again, plus this flange portion. Flange portion area is, so first focus on I. First focus on moment of inertia about x-axis. So parallel to x-axis side is 150 mm, 150 mm as it is. Multiply by this 20 mm height of that plane section, yes, 20 cube divided by 12 plus area is 150 into 20, area of that flange portion, and multiply by distance between original neutral axis and this flange portion neutral axis. So flange portion neutral axis is 120 plus 10, 130, and total T section neutral axis is 98.89. So 130 minus 98.89. And square of that term. So this Ixx is 20 into 120 cube divided by 12 plus 20 into 120 into 98.69 minus 60 square, 64725, 98.64, 64725, ninety-eight point six four. Again plus this term now, 150 into 20 cube divided by 12 plus 150 into 20 into 130 minus 98.89 square. It is 3003,496.3. So this Ixx is 6472598.64. So it is 9476094.94. That means 3 3. That means it is 9.5 into 10 raised to 6. mm raised to 4. So this is only moment of inertia about x-axis. And why we had taken this as a moment of inertia of that wave portion also, and plus area of that wave portion, and into distance between neutral axis, original section neutral axis, and that only wave portion neutral axis. Because of that, x-axis section is not symmetrical upward and downward, so that's why we had taken this all. Now see, now focus on that part. Why moment of inertia? Why we are finding that both moment of inertia x and y? Because in this formula we are interested to put least moment of inertia, and for y section C both This side also and this side also both are symmetrical, so no need to do this moment of inertia plus area into that between distance square. Just only calculate that moment of inertia of that one and wave and flange. So Iyy is easy calculation. Iyy is equal to 120 parallel side into 20 cube divided by 12 plus 20 parallel side into 150 cube divided by 12. So 120 into 20 cube divided by 12 plus 20 into 150 cube divided by 12. It is 57 point, okay, 5.7 into 10 raised to 6 mm raised to 4. So focus on which is least, Iyy or Ixx. So Iyy is least. So consider this Iyy for separate design. Now take this PC formula. PC is equal to pi square E. E is 200 GPa. In MPa it is 200 into 10 raised to 3. I is this 5.7 into 10 raised to 6. Pi square EI upon L square. See, L is 4 meter. That means 4000 square. See, remember this square. So this buckling load is pi square 200 into 10 raised to 3 into 5.7 into 10 raised to 6 divided by 4000 square. It is 7.03 into 10 raised to, wait, it is 703,209.31. This is in MPa. Calculate unit. This is in Newton per mm square. This is in mm raised to 4 and this is in mm square. So mm square get cancelled, only remaining square. This mm square also get cancelled. So unit is Newton. So this is 703.209 kilo Newton. So this is crippling load. That means buckling load 703.209 kilonewton for that T section. So it is higher load. See, 703.209 kilonewton. That means it is higher load. So this T section have that strength. 4 meter strut T section. Okay, that way our numerical completes. Only moment of inertia calculation takes a lot time, and either only putting values in PC equation and some basic understanding about that theory, that 2 points 2 ends hinge, that means its effective length is equal to actual length, like that. Okay, thank you very much.